Hi guys, welcome back to Ryan Study Corner. Today we are looking at our May-June 2024 paper. A couple of you have asked me to work through it to kind of gauge how your grade is or what your grade might look like. Personally, I didn't love this paper. It wasn't horrible, but I'm a calculations fan, so I would have been happy with a whole paper full of calculations, but my students seem to love it. They like the fact that it wasn't heavy calculations, and they said that they noticed that was a trend with all of the science subjects this year. So I don't know, you will tell me. So here we have our cover page. Let's skip into our first question. So we have identify the type of lens shown in figure 1. So here I have lens A. I could see this is a concave lens, and we could gauge that because it kind of looks like a cave at the side. That's how I always remembered it. So a concave lens. And B is a convex lens. I think you probably would have also gotten away with saying concave is a diverging lens. And convex is a converging lens. Now for the graph part. We have a student used the apparatus shown in figure 2 to determine the focal length of a lens. She adjusted the position of the lens and screen to form a sharp image on the screen. She measured the distance V, deduced the magnification of the object, and recorded her results in table 1 below. So we're seeing the diagram here, the object, well, the light source. Behind there we see where the lens is, we see the screen on the other side, and we have a meter rule, and that's what was used to measure the distance of the object from the lens and the image from the lens. Now we're seeing here they gave us all of the values for V. We're seeing they gave us the values for M. We didn't have to plug in any of the values, and they actually gave us the scale for the graph too. So using a scale of 2 centimeters to represent 0.5 on the y-axis, plot a graph of magnification, which is M, against image distance V on the grid provided. And 8 marks. 8 marks, we know first off, we have to make sure that we give it salt. Everything has to have a seasoning, our salt. We have to write our scale. We have to label our axes. We have to draw a line of best fit, and we have to put our title to get at least 4 marks here. This is before we even think about plotting anything, because plotting correctly will be the difference. So I'm going to copy this over here so that I can see everything on the graph page. They said use a scale of 2 centimeters to represent 0.5 on the y-axis. So 2 centimeters to represent 0.5 will be, let me zoom in a little bit. Point 5, 1, 1.5, 2, 2.5, 3, 3.5, 4. And that is my magnification axis. So I'll put magnification. We know magnification has no unit because it's image distance over object distance, so the unit cancels, or image height over object height, so the unit cancels. And then they didn't tell us what to do on our x-axis, but based on the values, I'm just going to use tens. So 10, 20, 30, 40, 50, 60, 70, 80. And this is my image distance from the lens measured in centimeters. Let me go back to make sure I didn't miss anything important. No, I didn't, so we're good to go. So let me give my graph some salt. I'll start with my scale. So on my magnification axis, 2 centimeters represents 0.5. On my image distance axis, 2 centimeters represents 10 centimeters. So we have this now, and remember, salt, I have my scale, I've already done my axes, my line of best fit will come after plotting my points, and my title. So I will say that this is a graph of M versus V, or you could say of magnification versus image distance from the lens, however you feel to phrase it. So let me start plotting my points now. Now before starting to plot your points, come up with your smallest division so that if you have to read in between the points, you know what is the value of each of the tiny boxes. So from here to here is 10, and there are 10 tiny boxes. So 10 divided by those 10 tiny boxes tells me that each tiny box is 1. So each tiny box here, or my smallest division on this side, is 1 centimeter. Do the same thing for the other axis. Here to here is 0.5, and there are 10 tiny boxes, so 0.5 divided by 10 is 0.05. So the smallest division here is 0.05. I don't know if y'all can see that properly. So I know how to count as I'm going through. Now my first point is M is 0.15 and V is 20. So V is 20 here and 0.15. If I know that the smallest division is 0.05, then I'm looking at 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5. So I'll come by 20, go up until I find 0.15, which 0.05, 0.1, 0.15 is right here. Then 30 centimeters and 0.65, so in line with 30, and then 0.65, we have 0.5 here, then oops, so 0.5 here, 0.55, 0.6, 0.65. It kind of looks like here. Then I have a 40 and a 1.2. So 40, and I'll have 1, 1.05, 1.1, 1.15, 1.2. So that's here. Then 50 and 1.85. So 50 and 1.85, I have 1.5 here, so 1.55, 1.5, I'm saying 1.5, 1.55, 1.6, 1.65, 1.7, 1.75, 1.8, 1.85. Oops. No, I kind of lost where I was. my next point is 60 and 2.35. So 60, and then I go up to 2.35. So 2.05, 2.1, 2.15, 2.2, 2.25, 2.3, 2.35, then 70 and 2.95. 2.95 I know will be right under 3, so that's an easy one to plot. And then 80 and 3.52. So because I'm seeing the ending and it's not ending with 0.5, I know right off the bat I have to kind of approximate for that one. So 80 is on the line, and 3.52, I'll have to put that in between 3.5 and 3.55. So it's going to be halfway between this. So these are my points. So I'm noticing that this looks like it's not going to be cutting our y-axis. It looks like it's actually going to be cutting our x-axis. So I kind of have to think about what does that mean to make sure that I'm not completely off. So I have to think about what's the relationship with the object distance and the image distance, and the magnification. Is there a time that the magnification could be 1? Is there a time that the magnification could be like 0? And I'm thinking there might not be a time. If we have an image, there won't be a time where we have both of them being 0, because that's really the relationship for something to pass through the origin. It has to be that they're directly proportional, so as one increases the other one increases, and also that if we could kind of extrapolate to a point and say, hey, when this is 0, this is 0. And then I'm kind of thinking that if there's a point where the image distance is 0, then there'll be no magnification, if that makes sense. I'm not seeing a possibility where we have one without the other. So maybe we just have to let our line cut here. But what I could do too is read ahead and see, okay, is there anything that they're telling me that implies anything else? And they're not asking about an intercept or anything like that, so I'm going to assume that I just have to draw my line of best fit here. So that kind of looks like it would be my best line of best fit. So this would imply that when there's no magnification, or when the magnification is 0, the image distance is whatever this is. That looks like 17.5 or something like that. So I have my graph, I have my line of best fit. Hopefully I've plotted my points correctly, and I have salt. So now I'm going back over to the previous page where they have calculate the gradient. So I need to find 2 points other than any of the points that I plotted, and I want them to be far-ish apart so that I could read off from them. So because I have the ability to zoom in, things will always look a little bit different for me than it would for you all. So I'll take, on top here, I'm thinking I will take this. That is what, 75. And my y value is what looks like 3.25. And then I have to look for something lower down here, that I could read off fairly well. I'm thinking I could maybe take here. Like here. I can't really tell for sure. But if I take there, then that looks like x is 22 and y is 2.5. And then I have to do my dotted line. We know like this actually counts for a mark, so we want to make sure and do it. Even though we see my dotted line is off, but you be better than me and don't do your dotted line off the line. So I have my points to do my gradient. I'll call the one at the bottom 22 and 2.5 x1 y1. 22 and 2.5, and the one on top, what's that, 75 and 3.25. This will be my x2, y2. Now I know gradient, which they're calling capital G, is y2 minus y1 over x2 minus x1. Plugging that in, I have y2 as 3.25 and y1 as 2.5, x2 as 75 and x1 as 22. So if I put this in my calculator, 3.25 take away 2.5 divided by 75 take away 22. So that gives me a gradient of 0.014. And I have to think about the unit. On the y-axis, I have no unit, so I could just put 1 here just for a place filler. On my x-axis, I have centimeters. So when we bring that centimeter on top, it becomes per centimeter or centimeter to the power negative 1. So that's our unit for our gradient. Now they're saying given that G is equal to 1 over the focal point or the focal length, calculate the focal length. So if G is 1 over F, it means that I could rearrange this, which would be F is 1 over G, which will be 1 over 0.014, which gives me approximately 70.67 centimeters. Now this one is a little bit tricky because this is one that we don't do much of. So we have figure 4 shows the full scale diagram of an object O, which has a height of 3 centimeters, and because it's a scale diagram, you can see it's 3 centimeters in height, or 3 units in height, and the object is placed 8 centimeters in front of a diverging lens L. So here's why it's tricky, because it's a diverging lens and we really always pay much more attention to converging lens. So they go on to say, given that the focal length of the lens is 5 centimeters, draw the ray diagram and find the image of the object. So, oh my goodness guys, my battery is low. So let's see. Let me see if I could do this before my battery dies. Now I'm going to put my focal point, since it's 5 centimeters, 1, 2, 3, 4, 5. I like to do it on both sides. So we know that we always show a lens coming off from the top going horizontally and a lens coming off going through the optical center. So first we have the one I'll do going straight across first. Now with a diverging lens, we know the focal point is the point through which the ray appears to diverge from. So I'm doing my ray diverging, but I know it has to appear to diverge from this point, so I'll do a dotted line back here. And then for my next line, I know it has to pass through the optical center. And when a ray is passing through the optical center, it's undeviated, or it doesn't bend at all, it just passes straight through. So something like this. So it means that where those converge, and I didn't do my converging properly, I should have made a more solid looking line so that we could see it clearly. Where those lines meet is where our image will be. So let me try to recreate my line here. Let's see, something that looks like this. So it means that our image will be a straight line in the middle here. Now I'm not sure if my line is like perfectly accurate. Did it actually pass through the point? Because I'm tending to believe that maybe it should have met on this line here. So I'm assuming that my line is a little bit off and maybe it was supposed to be here. They always give us a allowance too, so even if you were like me and your line is off, and let me erase a little bit to make sure. Yeah, if you're like me and your line is off, they give us generally like a little 10% grace. So my line has to pass through here. So let me see. So y'all should be able to use your rulers a lot better than I am here. So I'll just put it here because I keep getting mine to line up in the middle here. So I've drawn mine there, and that will be my image. Let me put I for image. So I've drawn it, and then they're saying record the image distance. So I'm going to say roughly 3 centimeters or 3.05 since mine was kind of in the middle. And if one thing here, we could round off to 3. I'm just going to put 3, but let me find the smallest deviation in case I wanted to like be hyper specific. If one unit here is 1 centimeter, like one box, and each box has 5 tiny dots, then it's like each tiny dot is 0.2. So because I'm getting something that's kind of halfway looking between 2 blocks, it's going to be half of 0.2, which is 0.1. So I'm thinking that this should be somewhere around 3 centimeters. Let me zoom in so that could look better. 3 centimeters or 3.1 centimeters, thereabout. State whether the image is real or virtual. Even if we had no idea what to do for the drawing, we could say that it's virtual because it's a concave lens, so we know it's going to give us a virtual image. Right. So now we have figure 5 shows a bottle filled with water resting on the ground in 3 different positions, A, B, and C. State the type of equilibrium for each of the following. So they mean stable, unstable, and neutral. The easiest way to think about it is that stable equilibrium means if we try to tip it over a little bit, it's going to try to go back into that equilibrium position where it's just standing upright. Unstable, easy way to think about it is if we try to tip it over, by default it's going to just fall over. And then neutral means that it's not going to be able to tip over that way, it might just roll along the table. So when we say it that way, we could kind of see right off the bat which one is which. So A is unstable equilibrium, B is stable equilibrium, and C is neutral equilibrium. Now describe the term moment of a force and state its SI units, and they're giving us a whole 4 marks, so we want to be as comprehensive as possible. I'm going to say the moment of a force is the turning effect of a force. I'm also going to give the formula. I'm going to give it in as words and in symbols, and I'm going to state the units so I'm sure that I'm covered. So the moment of a force is the turning effect of a force. It is calculated by moment is equal to force times perpendicular distance between the pivot and the line of action of the force, which we tend to write as F by D, and then I'll say the unit is Newton meter, just to be safe because it's a whole 4 marks. Then we have a moments question. So they're saying figure 6 shows a uniform meter rule. Once we see that word uniform, I was talking about this the night before exam with my Form 5 class. Once we see uniform, we know that means that the center of gravity acts at the very center of that body. So if it's a meter rule, it means the center of gravity is acting at that 50 centimeter mark. So it's balanced horizontally on a fulcrum, which is a fancy word for pivot, with a mass of 0.24 kilograms hanging from one end. And they gave us our diagram here. First thing, they want us to find the weight of that mass. Now we know weight is m by g. They're telling us that the mass is 0.24 kilograms and acceleration due to gravity is 10 newtons per kilogram. So 0.24 by 10 gives me 2.4 newtons. By taking moments, calculate the weight of the meter rule. So we'll notice that this is a whole 4 marks because we have a few things we have to do here. So 1, if we know that the weight is acting at the center, it means that the distance from here to here, because this might be the 0 mark on the meter rule, to here, because they didn't say anything about distance otherwise, that is going to be 50 centimeters. But we know with moments, we're talking about distance from the pivot to where the force is acting. So if this is 0.18 meters away from there, let's think about converting meters to centimeters here, or centimeters to meters. If I know this is 50 centimeters away, 50 centimeters, if I divide by 100, I get 0.5 meters. So it means the weight of this meter rule is 0.5 meters away from the end. So if this whole long distance is 0.5 meters, then the actual distance from the pivot to the weight is going to be 0.5. So let me write that down here. My distance is going to be 0.5 meters, take away 0.18 meters, which gives us 0.32 meters. So now we have everything and we just need to find the weight of the ruler. Now I know my formula is this is how I write the simplified version, the summation symbol. Sum of anti-clockwise moments is equal to the sum of clockwise moments. And I'll call the first force F1 and its distance from the pivot D1. Second force F2 and its distance from the pivot D2. So the first force is this mass here, which we already found the weight of, which is 2.4 newtons. And its distance from the pivot is 0.18. The other force is the weight of the meter rule, and its distance from the pivot is 0.32 meters. So to get W by itself, I want to send everything else over on the other side. And the only thing preventing W from being by itself right now is that 0.32. So it's involving multiplication here. When it goes over, it will switch to division. And I'll have 2.4 by 0.18 over 0.32 is W. I like to see it from left to right. So I'll switch it the other way and I'll say 2.4 times 0.18, oops, I made a mistake in my calculator there. 2.4 times 0.18 divided by 0.32 gives me a weight of 1.35 newtons. Part 3 says calculate the magnitude of the force of the fulcrum acting on the meter rule. So our default is once they bring like a few parts that relate to moments, one part is going to use principle of moments and the other part is going to use the other condition that must be satisfied for a body to be in equilibrium, which is the sum of the resultant forces is 0, or the resultant of all of the forces acting on a body is 0. Or the nice easy way I like to remember it, sum of upward forces is equal to sum of downward forces. So if I copy that diagram over here, so what are all of the forces we have acting here? I have this weight that is 2.4 newtons. I have the weight of the meter rule, which I just found to be 1.35 newtons. And then there'll be an upward force acting on the meter rule from the fulcrum. and I know the sum of upward forces must be equal to the sum of downward forces for something to be in equilibrium. So upward forces, which I'll just put as FU for force and upward, and downward is 2.4 plus 1.35. And if I add that, I get what? 3.75 newtons. So that is the upward force acting on the fulcrum. So now we're on to question 3. They're saying using arrows, match each mode of heat transfer to one correct description. Like when I look at this paper, while I don't like it, I'm happy because pretty much all of these things I discussed with my Form 5 physics class the night before exam. So I'm just so happy. But anyway, using arrows match to one correct description, which technically implies to me that there could be multiple that could work, but they want us to match to one. Now, one of the things that I noticed with this is that they might consider some of the things to be properties. One, conduction, we transfer heat through physical contact. Convection is transferring heat through a fluid, meaning a liquid or a gas, by bulk movement of the fluid. So it's within the liquid or the gas itself that liquid or gas is moving to transfer heat. And radiation is the transferring of heat through electromagnetic radiation. Anything else will technically be a property. So for example, with radiation, we see transfer without a medium. That technically satisfies that. But they might see it, maybe they'll see it as if you put that, you get the mark still, because that is a characteristic of that. But they might say that that is a property and not a description. So it could be that they have multiple options for getting it correct, or it could be that they put properties there to make it trickier for us so that we'll choose a property but not really a description, if that makes sense. So for conduction, I'm saying that this is the transfer of heat by physical contact, so I'm using this. For convection, transfer through liquids and gases, I'll use that. And radiation, I'll put transfer by electromagnetic wave, because I feel like that's a good description for each of them. Here I have figure 7, shows a section of a solar water heater which utilizes the greenhouse or glasshouse effect in its operation. So we see the whole diagram here, and it's saying briefly describe the greenhouse effect. So what's happening here is that high frequency, high energy radiation is coming down here. It's hitting the glass and it's traveling through the glass into this space here. Now, when it comes into this space, we see a black collector, because we know black absorbs a lot of heat. But some will still be emitted, because as everything underneath here heats up, it's going to have its own radiation now that it's going to give off. But its own radiation now is not as high frequency, or it doesn't have as much energy as the one that was coming in. So it will not have enough energy to pass through the glass, and it will remain trapped there. And that's essentially the greenhouse effect. So let me see if I can put that into words or into like good cohesive sentences. So I would say high frequency or high energy radiation is incident on the glass plate. the black collector plate and other components, which is really like the copper tubing and stuff, absorb heat, absorb the heat maybe. As they heat up, they now emit radiation. It's going to try to like emit it outward, but this radiation is low frequency, or I could say has a low frequency, has a lower frequency and less energy than the incident radiation so it is not able to pass through the glass, causing it to remain trapped. Further heating the internal components. Something along those lines, I think, would be a good description. Now we have the energy absorbed from the sun by a solar water heater is 360 kilojoules. 35% of the energy is transferred to 1.5 kilograms of water in the pipes. Calculate the final temperature of the water if its initial temperature is 30 degrees Celsius. So something is heating up, so we're automatically thinking E is equal to mc delta T, or E is equal to mc delta theta, however you feel to write it. Now we see the mass, which is 1.5 kilograms. We see C over here, which is 4,200 joules per kilogram per degree Celsius. We have to find delta T, or really we're trying to find one of the temperatures there. So my temperature, my initial temperature is 30 degrees Celsius. But I need to find E first to be able to use this. But they said in the question that this is how much is absorbed, but only 35% is transferred to the water. So I want to figure out two ways we could work this out. Either, if I think about it, I want to figure out how much is remaining. So I could say, well, 100% is 100%, but if only 35% is transferred, let me figure out how much is 35% that's coming in. So for some reason I read this first as 35% that isn't transferred, but 35% is transferred, so I'll have to find 35% of 360 kilojoules, and we know kilo means 1000 or by 10 to the power 3, so 35% of, and I'll slap on 3 zeros, or I could put by 10 to the power 3. So 35% of 360,000 gives me 126,000 joules. Now that is my E. So I have 126,000 joules being transferred to the water. It's 1.5 kilograms, C is 4,200. Now delta T is T2 minus T1. But we always put the larger temperature first because we're looking at the temperature change. So we keep it in like the kind of positive area. So I'll put the second temperature, the final temperature will go first because that's larger. And my initial temperature was 30. So to rearrange things, I could send 1.5 and 4200 onto the other side. They'll switch to division, so they'll come underneath here. So 126 divided by 1.5 by 4200, which gives me 20. So if 20 is equal to T minus 30, I'll send the negative 30 over, it'll become positive. So 20 plus 30 is equal to T. So T is 50 degrees. And they didn't really specify what unit they wanted it in, but I'll just leave it as this form rather than converting to Kelvin. Explain why the pipes or tubes are made from copper. Copper is a good thermal conductor. So one, when heat hits it, it's able to heat up the entire tube of copper fairly quickly, and it's able to transmit that heat through it into the water. So I'll say that copper is a good thermal conductor. And because it's 2 marks and so many lines, I'm feeling like I need to put more information. Again, why I like calculations over explanations. So I would go on to say that copper is able to transmit thermal energy throughout the pipe easily, and also transmit thermal energy to the water within it easily. So anything kind of along those lines. Now for number 4, I have figure 8 shows a circuit diagram with a low voltage power supply circuit, which can be used to test whether a given material is a conductor or an insulator. So based on how this looks, I'm seeing a lamp here and I'm seeing 2 connectors. So we would put our material there and we'd close the switch. If the bulb lights, it means that it's a conductor because it means that that material that we put in allowed current to flow through it. What I would also say too, just to be on the safe side, I would probably say then take the material out and flip it the other way as well to see if current will flow. Just because I'm thinking, what if the thing that we're plugging in is something like a diode? I don't know, maybe I'm overthinking this, but I would still turn it on the other side too. So I would set up apparatus as seen above, placing the test material through the where did I get through from? Placing the test material between the contact or connectors if the bulb lights once the switch is closed, it is a conductor, then I would say turn the material in the other direction, and close the switch again, ensuring that the bulb lights. So I would just say put it both ways. Name one material that is an electrical conductor and one which is an insulator. So I think the more common ones would be oops. So I think the more common ones would be something like saying copper or aluminum, and then probably the more common insulator would be wood, but we know you could use plastic, rubber, or whatever. On the diagram, mark the direction of electron flow. So we know electron flow goes from the negative terminal to the positive, so it's going to go this way. Now, figure 9 shows a circuit which has a combination of 4 resistors and an ammeter. Calculate the reading of the ammeter when the switch is open. So when the switch is open, then current is flowing through here only, because we know it can't flow while it's open. So technically all of these resistors are in series when it's flowing this way. So the reading on the ammeter, first I have to find the resistance. So total resistance in a series circuit is R1 plus R2 plus R3. So that is 1 ohm plus 6 ohms plus 3 ohms, which gives me 10 ohms. But what they're asking for is the current. So I have to use V is equal to IR, and when I rearrange, I will be V over R. And the voltage we're seeing is 12 volts, and the resistance is 10 ohms, so that gives me a current of 1.2 amps. Then for part 2, they're saying what about when the switch is closed? So when the switch is closed, technically these two are in parallel, so we have to work out both of them in parallel and then add that on to everything else. So in parallel, because it's only 2, I could use product over sum, or I could use 1 over RT is equal to 1 over R1 plus 1 over R2. But I'll use RT is equal to R1 by R2 over R1 plus R2, which is 6 times 3 over 6 plus 3. 6 times 3 is 18, 6 plus 3 is 9, 18 divided by 9 is 2. So the resistance there is 2 ohms. So it essentially is like, let me do a little sketch of that. So we could visualize what's going on. It's like if I erase here, and instead of all of this, it's just one resistor that has a resistance of 2 ohms. So now it looks like a series circuit, where I could say that now the resistance here is R1 plus R2 plus R3, which gives me 1 ohm plus 2 ohms plus 3 ohms, which gives me a total of 6 ohms in the entire circuit. And remember, we saw above that I is equal to V over R, which the voltage is still 12 volts, but now R is 6 ohms. So 12 divided by 6 is 2 ohms. So that was a nice little calculation there. Calculate the power dissipated in the 1 ohm resistor when this switch is closed. So power lost, and we're talking about resistance, I'm thinking we'll be using P is equal to I squared R. When the switch was closed, I saw that the current was 2 amps, and they're specifically asking us about the power lost as it's passing through the 1 ohm resistor. So 2 squared by 1, 2 squared is 4, 4 by 1 is 4. So we have a power loss of 4 watts as we're passing through there. Now determine the electric field. So this is the region around a charged body where another body, it could be charged or it could be neutral, where another body would experience a force. So this is the region around a charged body where another body, you could put another charged body, or you could put uncharged, because technically a neutral body can experience some sort of force depending on how great the potential difference and stuff like that is, or how large the charge is, where another body experiences a force. Figure 10 represents the electric field between and around two charged bodies. State the type of charge at object A. So electric fields go from positive to negative. So for object A, it's moving out of A, meaning from A. So it means A is positively charged. Explain why a polythene rod, when rubbed with fur, becomes negatively charged. So what's essentially happening here is that electrons from the fur become delocalized and are transferred through friction over to the polythene rod, causing the polythene rod to have a surplus of negative charges, causing it to be negatively charged. So electrons are delocalized and transferred from the fur to the rod by friction, causing a surplus of electrons on the originally neutral or uncharged rod. This surplus of electrons causes a negative charge. Right. So a magnetic relay is used to switch on a circuit carrying a large current. Figure 11 shows an electromagnet used in a magnetic relay to operate the starter motor of a car. explain how the magnetic relay can be used to operate the starter motor in figure 11. So what's going to happen is that when this switch is closed, current is going to flow through here, and we have a soft iron core, meaning there's a magnetic field that already formed as current is flowing through the solenoid, and because it's wrapped around the soft iron core, then the magnetic field becomes stronger. On the other side now, on the secondary or output circuit, I'm seeing that I have a soft iron armature here, meaning that the magnetic field created here will cause this piece of iron to be attracted to it, because one thing we know is that only magnets repel each other, but magnetic materials will always be attracted to the magnetic field. So it means this piece of iron will be attracted to the magnetic field, meaning it will pull this way, and as it pulls to the left, it closes the metal contacts, completing the circuit so that current can flow, causing the starter motor to start running. And then once we open the switch so that current can't flow through here any longer, then there's no magnetic force pulling this closer, so this spring will pull the contact back, opening the circuit so that the starter motor will turn off. And that's what we're going to try to put into words now. So I have once the switch on the primary circuit closes, the current through the coil creates a magnetic field. This magnetic field is strengthened. I don't know if I spelled that correctly, by the soft iron core. This magnetic field, or this strong magnetic field, because it's stronger now, attracts the soft iron armature, causing it to close the metal contact, completing the circuit, and allowing the starter motor to start running. Once the switch on the primary coil or primary circuit is open, there is no longer a magnetic field to keep the contacts closed, and the spring pulls or pushes the iron, and the spring mount, if you want to call it like, the whole correct name. The spring pulls the iron back to its original position. That's along the lines of what I would put for that. Now, figure 12 shows a wire connected to a zero center galvanometer. The wire is placed between the poles of a permanent magnet, and they're saying state what is observed on the galvanometer when the wire is moved in the direction shown by the arrows. So a current is going to be induced, so we're using Fleming's right hand rule. FBI, force or movement, B for magnetic field or magnetic flux, I for induced current. Now, first they said if it's moving parallel to the magnetic field. So a current is only induced if the conductor is cutting the flux lines, as in cutting those lines that we see going from north to south. So it means in the first instance, there's no deflection. Now, if it's moving upward, my magnetic field is going from north to south. So FBI, the current is going to come out of the page toward me like here. So when that happens, it's going to go this way to continue to flow this way. So this will deflect to the right. Or deflection to the right. Next they say downward through the magnetic field. So FBI, it's moving down, force is down, magnetic field is north to south. I means it's moving this way now into the page, which is here. So it's going to come here, try to flow this way, so it will deflect to the left. Now for the last one, another question that I was not a fan of because of the fact that it requires explanation and discussion. So a single nuclear fission reactor could produce most of the electricity requirements for many Caribbean countries. This is like literally the one thing that my Form 5 physics class and I did not discuss, which I'm disappointed in myself with because it came last year. And it's something that so rarely comes. I really was not expecting this to come this year. So, in any case, I mean in this sense of it, like how renewable energy came, I didn't expect nuclear energy to come like that or renewable energy to come like that. So it was a surprise. State two arguments against building such a nuclear reactor in one of the larger islands of the Caribbean. So I would just always use safety here as the against. So I would say that Caribbean islands, even the larger ones, it's really difficult for us to be able to store the amount of radioactive waste that it's produced, just because we're so small. And also if there's an accident or if there's a leak, it really affects the entirety of the island or the amount of water sources that we have everywhere, that it's going to contaminate the water sources as well and whatnot. So you will tell me if you had any others, because these are really all that I could think of. So one will be that Caribbean islands generally too small to store significant amounts of radioactive waste. Then I would also say that if there's an accident or a leak, it affects the entire island. So if there is an accident or leak, the entire island will be affected. Maybe you could say things like startup costs, shutdown costs, maintenance costs, whatever you think makes sense. Give one argument to support the building of such a reactor to produce the electricity required for an island. So the biggest thing for me is socioeconomic, I'm thinking, because then it removes that island's dependence on oil and gas importation, so they have energy security then. Having a reactor, my spelling there is in a mess, removes the dependence on oil and gas imports, thereby causing or increasing energy security. Then we have defined the term radioisotope. So a radioisotope is the same element with a different number of neutrons. So this is the same atom or element with a different number of neutrons. Then radioisotopes have useful applications in the fields of medicine, agriculture, and industry. Choose two of the fields above and describe one useful application of radioisotopes in each. So I'll do it for all three so that depending on which one you did, you kind of have a gauge of what you could have used. So starting with medicine first, because that's the easiest one. So I'll say diagnostic imaging. So like PET scans and that sort of thing. They use the radioisotopes to be able to take pictures of what's going on in our bodies. Then tracers, where they inject it into wherever to see whichever part of our body has some sort of blockage or something like that, so that they could see through their scanners where there's the blockage. I'll put medical tracers. We could say cancer treatment. Then for agriculture, tracers in irrigation systems to see like where there's a leak or that sort of thing. In any sort of research, they could use tracers to investigate like the uptake of fertilizers and water and whatnot into plants. So we have tracers here again, tracers for leak detection, irradiation of food, like to get rid of E. coli and salmonella from unfood services, and that's really all I can think about. So let me put that. Irrigation leaks tracers, or maybe you could just put tracers. What was the next one I said? Tracing the uptake of fertilizers and whatnot. And the next one was irradiation. To prevent foodborne diseases. The next one was industry. So maybe you could decide where you wanted to put something like carbon dating. I'm not really sure where, because technically it could fit under industry, I guess. So one, smoke detectors. Then we use this to measure like the thickness in production plants and whatever. So like thickness of paper, etc., to measure the thickness of paper, I really should say. And then tracers, finding leaks in pipelines, whatever. So still tracers. So anything along those lines, and of course tell me if there's any else or any others that you used. Now the letters P, Q, R, X, and Y represent 5 different nuclides. Determine which have identical mass numbers. Mass numbers are the one on top. So P and R, because they both have 40 as the mass number. Where, how many neutrons are in the heaviest nuclide? So the heaviest nuclide will be this one. Now the 238 is the mass number, which is the number of protons and neutrons. And then the 92 is the atomic number, which is the number of protons. So if we subtract those two numbers, we'll get the number of neutrons. So number of neutrons is equal to 238 minus 92, which gives me like 146 neutrons. Which pair isotopes? We just saw that isotopes are the same element with a different number of neutrons. So we're looking for elements where the atomic number is the same and it's only the mass number is different, and it's different by like a small amount, like 1, 2, 3, that sort of thing. So I'm seeing same atomic number here, mass number of one is 39, mass number of the other is 40. So P and Y are isotopes. Now, in an experiment to determine the half-life of a radioactive isotope, the initial count rate of 16,000 counts per minute was recorded. After 100 seconds, the new count rate was 1,000 counts per minute. Use the information given to calculate the half-life of the isotope. So the half-life is the period of time taken for it to decrease by half. And we don't know what the half-life is, but we're trying to see how many half-lives are in 100 seconds so that we can figure out what is the half-life. So I start off with 16,000 counts. Now after half-life period, it will drop to half of that. So half of 16,000 is 8,000. After another half-life period, it will drop to half of 8,000, which is 4,000. After another half-life period, it will drop to half of 4,000, which is 2,000. And after another half-life period, it will drop to half of 2,000, which is 1,000 counts. So 1, 2, 3, 4 half-life periods. So I could say if 4 half-life periods took 100 seconds, then 1 half-life period will take 100 divided by 4, which gives me 25 seconds. So that is the half-life of this radioactive substance. And that's it. So that's it for our May-June 2024 paper. Tell me, what do you think in the comment section? Did I make any mistakes? Did you do something different? Are you less anxious now about your results? Now, we're in the home stretch, only paper ones to go, so good luck in your paper ones, guys, and I will see you all in the next past paper. Bye bye.